Friday into April 2023. About 2 in the afternoon, sunny, bright, clear, and warm. Preternaturally warm, unseasonably warm, global warming warm. Record highs. So today, what we've been reading is Albert Einstein's chapters on physics in his books Out of My Later Years by Albert Einstein. And they've been quite remarkable in terms of his definitions of special relativity and general relativity, right from Einstein's mouth, right from the horse's mouth, the authentic, the original, the authoritative. So with these, as of course to his principles of relativity, and the L principle, light's principle, is being one of his key establishments in all mathematical interpretations. Light speed is a constant. In terms of the coordinate settings, that absolute motion does not exist. Each coordinate setting in each frame is its own. Then in terms of whatever is shared, then that's part of a larger frame. It's like so. And as with regards to Newton's gravity, Einstein gives a great defense of Newton's gravity, his theory of. And then also that can be written as it is possible by always being able to exchange and template any specification with the alternatives and arguments, for example, the complements or opposites, evaluating same for validity and verificationality and truth. Einstein gives a very proper defense of himself in that sense, that his own notions of the total field theory are extra relativity. And that means beyond, outside, inclusive, though, of relativity, much as he claims it so for Newton. Now, one of the ideas why gravity isn't a force and it doesn't exist in the theories of the day is because it would violate conservation of energy, because Newton's theory would have that it's constantly doing work. You need two massy bodies to pull themselves together. In Einstein's theory of general relativity in space-time, there's the idea that according to the mass of a body, and that there's a relativistic mass, at least in the rotational, that it would just distort space-time, and then everything follows the principle of least action on the same sort of path as so predicted by Newton's laws, with regards, though, that there's added mass-energy equivalency that is defined by mass, and the extent of bodies, or the density of mass, as with regards to the special singularities of mass and density in a small space, or the gravitational singularity, or black hole, which is defined as a region so dense in mass that its gravitational attraction, so modeled, results that everything within its region falls into it. Any orbit that decays to it is as essentially closed loop. That anyway, changing and distorting the space-time is presumed free in a sense. It's like, well, we don't call that violation of conservation of energy because nobody ever said that the gravitational space frame would straighten itself back out. But there's as well the conceit that, well, yeah, as far as it goes, every change anywhere in the geodesy is always instantaneously evaluated from moment to moment in each place altogether, as with every extra local thing that forms its entire field of the curved space-time, that also that's left out. So this is among reasons why there's still a place then with relativity on the one side, governing the parallel transport of light-like behavior by special relativity, after governing behavior of matter's transport with general relativity in terms of mass-energy equivalency, and the gravitational field equations, which also include the cosmological constant about the highly contrived or various. Then on the other side, there's quantum mechanics, and the quantum mechanics is the behavior of the discretization, or the particles as small. It's a particle model that we imagine our elementary physics as of atoms, the uncuttable, then the subatomic physics, another yet conceit too, that our discretization essentially is a partial and incomplete metaphor, that it so results that what there is above it a continuum mechanics. The figuring out how to have gravity back in the middle again then makes it so that this alternative concepts which must be explored are these supermodels of flux and supermodels of flow. Now, the first time I heard the term flux, I imagine it was in the context of the soldering iron. And rosin or flux is an attachment to the tip as of the rosin is for the flux. Rosin is attachment to the tip of the soldering iron, where the soldering iron then is used to connect to a piece of solder, and then at a joint between two metallic things, that the soldering iron melts the solder, and thus that a flux makes it so that it flows around that. And it so results that then, removing the heat as so input by the constant input by the resistance of an electrical current through the soldering irons heating element, has it then that the solder freezes in a sense, or it leaves liquid form and forms a metal with the metal that it is with. Some people say metal is one giant atom, but that's because it's molecular, and this is about the current and stuff through it. So anyways, that was my first introduction, or what I ever remember of what was flux. And then later, though, it's as with regards to flow. And so flow is, I kind of frame anything that's governed by general relativity, and the bradyonic, slower than light, is flow. And anything that's modeled by light's absolute maximum speed of any signal in a vacuum by itself, massless, its image, it's tachyonic and flux. And so then this still fits pretty well with these are common definitions. These are not unconventional definitions. They do not have any necessary attachment to any particular things that make them anything less than free and fair nomenclature for these things in physics throughout the field. It's very important when choosing words, discussing sciences and other common concepts, that it's not nonsensical contradictions in terms or made up words. So the making up of words that fit is a very important boundary between comprehensive detail and what's called glossolalia, or word salad, or word soup. The idea that word soup is a special form of word salad that's good for you, whereas word salad is nonsensical utterances. So anyways, flow and flux then represent how things disperse in the dissipation and attenuation as well, that they go as about and around, while the restitutive and oscillating and centralized is about how things, if they waver, that they return, like a pendulum, like a resonating fork of the tuning fork, or a wave motion, or any kind of periodic activity or action or effect, or the rotational, vis-a-vis the linear, which always maintains its own relative motion to everything else, its own little absolute frame. Then with regards to what happens when it enters orbits and leaves orbits of other objects with respect to each other and ad infinitum, all through the points in space-time, all through the model of universe. So that being not so unusual, Einstein went on in his discussion that had been reading it about E equals mc squared, his most famous equation. And now, if Einstein is kind of the most famous public face of the atomic era and the era of the atom bomb, then in this equation, the most fundamental, benchmark of scientific understanding of the power of it. Then there's Oppenheimer, and Robert Oppenheimer was a physicist, kind of like Wernher von Braun, or after World War II is a separate story, but before it is that on the inside of something like the Manhattan Project, or that, is that he's basically the outward-facing person in that. And so I don't know too much about his life or the surrounds or this and that, but it's that's the kind of cultural thing that's the esoteric for the exoteric. Einstein is the exoteric. In fact, he's held up as the greatest lion where a lion is a noble animal and not a savage beast that eats everything, a vicious predator of a sorts of the feline variety. But Albert Einstein is a hero. Albert Einstein is a great hero for science, and both the spirit and the soul of science, with the spirit of science as for scientific advancement, and for the soul of science as with feeling. So going on then into his discussion of E equals mc squared, then it was described its mathematical fundamentals and why, as Einstein put it, it's inexact. It's not exact, it's inexact, as part of his careful, if not necessarily professed, success as a grandiose hedge. So then, in reading the following chapters, and there was about gravity, space, and time, and there was quite a discussion about, why does physics today still not have a theory of gravity? Well, as mentioned, it's because it would need these mathematical models that express this tachyonic flux, that would express for something like the particle and waves how resonance works. And this is detailed in things like this book about macroscopic theories of matter and fields, a thermodynamic approach, and theory of unimolecular reactions, vis-a-vis atomic reactions that are, single and reflect actions only on the level of the atoms and their bonds, but of the molecules. And that these are the sort of things in terms of nuclear physics. This is more of our subatomic physics, and the stratum beneath this is a book by Werner Heisenberg. In terms of these Markov processes and potential theory, for example, if we've been discussing when they have their non-classical and super martingales and the infinite and the quasi, the pseudo, and the degenerate, meaning the fully more fundamental and the sub atomic. That defined by the super classical regimes, which so result why it comes back into real classical space, to explain why, given these super classical explanations that can build a model for extra local falsifications, that it's not difficult to arrive at all the classical derivations, like Newton's inverse square. What also happens to look just like inverse square attraction is actually as simple as a falling together according to mass in density in regions, as occluding otherwise the tendency to drift not together. These sorts of complements then make up for all the sums in terms of potential theory and the harmonics, the hyperharmonics, that add up to these fully higher level theories of fields and these sorts of things. So, then here I'm leafing in Werner Heisenberg's books, Nuclear Physics by W. Heisenberg, director of the Max Planck Institute of Physics, Göttingen. Göttingen, Germany, is a traditional center of learning and development in the forefront of science. I'll look at that in a minute. So Einstein, there's another chapter yet for us to read here, Physics and Reality. This is chapter 13, and as we've just read about his theory about time, space, and gravitation, and his theory of principles, and why he finds that, according to his philosophy of science and his philosophy of mathematics and his philosophy of physics, satisfying, and ended with his great defense of Newton and Einstein. And that Einstein, my perception of Einstein's two greatest contributions are mass energy equivalency, the concept, and the development, the outlay, and its placement in the fields ready to pick up by anybody who needs to use a relativistic framework, and the cosmological constant as not defined, but present. So, chapter 13 says Physics and Reality. Section 1, General Consideration Concerning the Method of Science. It has often been said, and certainly not without justification, that the man of science is a poor philosopher. That's an empiricist. The empiricist is happy and done. An engineer can be done and only needs their platform and their planks, not the foundation necessarily. Why then should it not be the right thing for the physicist to let the philosopher do the philosophizing? Such might indeed be the right thing at a time when the physicist believes he has at his disposal a rigid system of fundamental concepts and fundamental laws which are so well established that waves of doubt cannot reach them. But it cannot be right at a time when the very foundations of physics itself have become problematic as they are now. At a time like the present, and this would have been about 1936 or so, when experience forces us to seek a newer and more solid foundation, the physicist cannot simply surrender to the philosopher the critical contemplation of the theoretical foundations, for he himself knows best and feels more surely where the shoe pinches. Looking for a new foundation, he must try to make clear in his own mind just how far the concepts which he uses are justified and are necessities. The whole of science is nothing more than a refinement of everyday thinking. It is for this reason that the critical thinking of the physicist cannot possibly be restricted to the examination of the concepts of his own specific field. He cannot proceed without considering critically a much more difficult problem, the problem of analyzing the nature of everyday thinking. And not just everyday thinking, but thinking writ large, W-R-I-T, writ large. The concept. On the stage of our subconscious mind appear in colorful succession sense experiences, memory pictures of them, representations and feelings. In contrast to psychology, physics treats directly only of sense experiences and of the understanding of their connection. Here we frame that more in terms of models and interpretations and observables in a framework of reproducibility. But even the concept of the real external world of everyday thinking rests exclusively on sense impressions. This is arguable. Now we must first remark that the differentiation between sense impressions and representations is not possible, or at least it is not possible with absolute certainty. It's fair. It doesn't explain away that there can be Platonic ideals and all this sorts of stuff that derives from deduction that one can have as written down in a sense and put away, and there when you return for it and or for someone else to find. But in the memoryless, it's so, or for the newbie. With the discussion of this problem, which affects also the notion of reality, we will not concern ourselves, but we shall take the existence of sense experiences as given, that is to say, as psychic experiences of special kind. I don't know if he's introduced the word psychic before, and it relates to the psyche, which is a special concept of the mind, the theory of mind in the psyche, from which stems psychology and the psychological. I believe that the first step in the setting of a real external world is the formation of the concept of bodily objects and of bodily objects of various kinds. Out of the multitude of our sense experiences we take, mentally and arbitrarily, certain repeatedly occurring complexes of sense impression, partly in conjunction with sense impressions which are interpreted as signs for sense experiences of others, and we attribute to them a meaning, the meaning of the bodily object, or substances, sensata, qualia. Considered logically, this concept is not identical with the totality of sense impressions referred to, but it is an arbitrary creation of the human or animal mind. On the other hand, the concept owes its meaning and its justification exclusively to the totality of the sense impressions which we associate with it. One concept of this is the context is that in the universe, a thing is defined by everything that it is not. If that thing were removed and all that was left in the whole universe was the whole where it was, it would be the same whether it was there or not, because it's defined, everything that it is, by everything that it is not. this makes for a universe with at least two things in it. The second step is to be found in the fact that in our thinking, which determines our expectation, we attribute this concept to the bodily object as significance, which is to a high degree independent of the sense impression which originally gives rise to it. This is what we mean when we attribute to the bodily object a real existence. The justification of such a setting rests exclusively on the fact that by means of such concepts and mental relations between them, we are able to orient ourselves in the labyrinth of sense impressions. So this is again still for a philosophy of science and a philosophy of reasoning agents' access to the reproducible experiment with models what can be attached to sensory input qualia, or the phenomenological and the phenomena, for the noumenological, for the noumenon, the noos, the noosphere, the thinking place. And there's some reference to the labyrinth, and so here the labyrinth is a couple different things. It's a labyrinth of the maze and the monster, and it's the labyrinth of the paradise and the gardens. And there's talk about the Jerusalem, the Crystal City, and the garden, and then Byzantium and the same thing, and whether Jerusalem and Byzantium are to mean the same thing. That on Earth they do not generally, but that they have the same symbols. So anyways, these notions and relations, all the free statements of our thoughts, appear to us as stronger and more unalterable than the individual sense experience itself, the character of which, as anything other than the result of an illusion or hallucination, is never completely guaranteed. On the other hand, these concepts and relations, and indeed the setting of real objects and, generally speaking, the existence of the real world, have justification only insofar as they are connected with sense impressions between which they form a mental connection. Now, some will have that there exists a continuum, it might as well be time, there is a universe, and it's all one thing. But this is also a notion of an independence from that. And that it's an abstraction. So it's an abstraction. The very fact that the totality of our sense experiences is such that by means of thinking, operations with concepts, and the creation and use of definite functional relations between them, and the coordination of sense experiences to these concepts, it can be put in order. This fact is one which leaves us in awe, but which we shall never understand. Here, the very notion of the word understand means different things to different people. And some people it means accept, and some people it means to grasp, and for other people it means to thoroughly comprehend a subject, or for others that it represents an exception and why they understand that something that otherwise would just be known. So understand is a really underdefined word, and I try to avoid it because it's usually in the sense of something that is not common but is at best a tenuous sort of compromise, which I try to avoid because it represents failure. Understanding. The very fact it can be put in order. This fact is one which leaves us in awe, but which we shall never understand. I just find that it's something that can be accepted, and is accepted. It's sort of understood because then it becomes that this state of one's own limitations is not that big a deal, and otherwise one can appreciate all the benefits of that without being so worried about it. So I do not see that as a bad thing. What she sees as maybe something that is a sign of disorder. It can also just be seen like in this context where it's everything is not. It's the opposite. Einstein. One may say the eternal mystery of the world is its comprehensibility. That's like the greatest paradox. There are none. It is one of the great realizations of Immanuel Kant that the setting up of a real external world would be senseless without this comprehensibility. Immanuel Kant had to both defend Platonism to establish grounds for reason in the Enlightenment thinkers, but also defend the adherence to the utter fundamental principles of presentation of the sociological construction of the laws of authority in belief of the church. And so that was important to him. While it's still to be reflected that over time, as it's possible that the whole society gets more of an ability to accept science and to be cognizant creatures in it, and they would reject otherwise being told, like, these are your sanitation laws because it's the law. These are your marriage laws because it's the law, and ... It so follow that it's built up again higher over that yet the overarching goal of religion or church can still be to establish that frame as up above. So over time and historically, what Kant would say then and defend, he might have a much more extensive position about its emergence and its presence in a modern day Kant. And it's kind of similar with Einstein. And with anybody who expects to speak to the people broadly in this kind of thing. In speaking here concerning comprehensibility, the expression is used in its most modest sense. It implies the production of some sort of order among sense impressions, this order being reproduced by the creation of general concepts, relations between those concepts, by relations between the concepts and sense experience, these relations being determined in any possible manner. Now that can be read in any at all or any and every. There's a great disambiguation to be done for the universal quantifier, for any, for each, for every, for all. In some cases, for some considerations, they're the same. They do not need disambiguation. In other cases, it's ambiguous when one says for any, one says for every, one says for each, one says for all, whether or not each and all of those apply for any and every occasion. Now, I've just split it up into these four cases of sorts for universal quantification because those are the most readily accessible words which have at least a slight variation in meaning in English. But the idea is that those very well and directly apply what is the act or the fate or the opus or the stroke of reasoning and logic about them in terms of the predicates and the connectives and with the implication, as after causality and the deterministic, why that kind of thing can help disambiguate whether Einstein by any means the least possible grasping straw or every. Of course, by his science, he means every, because any result which contradicts a scientific proof has basically invalidated the theory. And so we can read this as generous and as well specific. Any sufficiently expressive phrase has at least one meaning. It is in this manner that the world of our sense experiences is comprehensible. The fact that it is comprehensible is a miracle. There are no paradoxes. In my opinion, nothing can be said concerning the manner in which the concepts are to be made and connected, and how we are to coordinate them to the experiences. In guiding us in the creation of such an order of sense experiences, success in the result is alone the determining factor. All that is necessary is the statement of a set of rules. This is the model, since without such rules, the acquisition of knowledge in the desired sense would be impossible. The qualia only gather into objects with reference in these models. One may compare these rules with the rules of a game, in which, while the rules themselves are arbitrary, it is their rigidity alone which makes the game possible. Rules to general lack of order are simply enough exceptions and establish organization and order. By their statement is what otherwise that they establish a basis for contradiction and non-contradiction. One may compare these rules with the rules of a game, dot, dot, dot. While the rules themselves are arbitrary, it is their rigidity alone which makes the game possible. In a broader zero-sum game. However, the fixation will never be final. Here we might talk about first cause and final cause and first principles of an ideal theory where that God's own theory or the most on high is essentially modeled as a perfect theory with no paradoxes. It will have validity only for a special field of application, i.e. there are no final categories in the sense of Kant. And so here he's just expressed that physics is an open system, and insofar as we have tractability in our realm, it's not going to be complete. This is fine and fair. This is just saying that we can still have a successful physics and a successful theory without it being the theory of everything, because that would be more and more difficult to achieve. It does not say that at some point in time, pretty much science has arrived at a great bulwark and body of theory, and that's it. It's great. The connection of the elementary concepts of everyday thinking with complexes of sense experiences can only be comprehended intuitively, and it is unadaptable to scientifically logical fixation. I would disagree. But it's not necessarily tractable to completely adapt it. That doesn't mean it's not adaptable. And here we might reflect the difference between the negatory of achievement and the negatory of attainment. Just like the notion of the limit is it goes to, and some have that it achieves the limit. The limit is the sum. Other that the limit goes to the sum. Or the sum goes to the limit. But carrying on, the totality of these connections, none of which is expressible in notional terms, none of which, another universal, is the only thing which differentiates the great building which is science from a logical but empty scheme of concepts. By means of these connections, the purely notional theorems of science become statements about complexities of sense experiences. And here the usual idea, and Einstein is very much a proponent of mathematics in his models. He definitely says that mathematics is a pure thing. It can live kind of on either side of this, is the practice or the applied or the ideal. By means of these connections, the purely notional theorems of science become statements about complexities of sense experiences. And furthermore, they embody our philosophy of science with models and the notion of the relativity of experiment, that anybody can achieve the same results of theory according to physics, given other things constant. We shall call primary concepts such concepts as are directly and intuitively connected with typical complexities of sense experiences. All other notions are, from the physical point of view, possessed of meaning only insofar as they are connected by theorems with the primary notions. These theorems are partially definitions of the concepts, and of the statements derived logically from them, and partially theorems not derivable from the definitions, which express at least indirect relations between the primary concepts and in this way between sense experiences. Their axioms. That's my edit. Theorems of the latter kind are statements about reality or laws of nature, i.e. theorems which have to show their usefulness when applied to sense experiences comprehended by primary concepts. So here Einstein's law of nature is his law that he's using to judge, and a little bit different is the model's laws, or its rules. Other people will call the rules of the model the laws. And here he's just saying that otherwise that these are the rules of his calculations. So that it also gets into the constructive versus the principled, and why are they same and not the same. When he says principle, does he really mean the intuitionistic as the mathematicians have it? Yeah. But he relates what are his laws of nature as of his qualia and his sensory experiences. It's his law sense. Like he has physical senses, he has object senses, like number sense and word sense, and the sense for his physics, his sensibility of his physics, the law. The question as to which of the theorems shall be considered as definitions and which as natural laws will depend largely upon the chosen representation. It really becomes absolutely necessary to make this differentiation only when one examines the degree to which the whole system of concepts considered is not empty from the physical point of view. Einstein's careful objectiveness as a scientist is to make sure that when reading Einstein and not just his theory, that he presents himself as impartial and can only vouch for what tools you may have, not necessarily what you may bring. And he does not deny otherwise these things, only saying that all you can expect and ask from him is that this. And that's fair, because otherwise he would be giving you the rest of a theory also, which some has as variously non-scientific, or so on. So this chapter is about physics and relativity and So then going on, this next section here, the next piece of section 1, I may not get through this, the stratification of the scientific system. The aim of science is on the one hand a comprehension as complete as possible of the connection between the sense experiences in their totality, and on the other hand the accomplishment of this aim by the use of a minimum of primary concepts and relations. Emphasis the authors. By the use of a minimum of primary concepts and relations. So this is about the paucity and efficiency and economy of our fundamental objects, which have to add up to everything else. And so as we were talking about last time, it's that it's energy. We have conservation of energy and maybe momentum. But really, we can have that also in these complementary concepts in the fields and our forces, mass and charge, and for those quantities that is, yes, they interchange through energy, but it's not necessarily the aim to minimize these primary concepts when it's the self of primary concepts, their complementarity. So otherwise, though, in any particular application or domain, the idea is to abstract everything else away and get a symbolic form and crunch it. That's also for the applied. That there's very much so that the pure and applied are two different things, and that the fundamental elements become all that what's available to the applied. Seeking as far as possible logical unity in the world picture, i.e. paucity in logical elements. Science concerns the totality of the primary concepts, i.e. concepts directly connected with sense experiences and theorems connecting them in its first stage of development. Science does not contain anything else, or everyday thinking is satisfied on the whole with this level. Such a state of affairs cannot, however, satisfy a spirit which is really scientifically minded, because the totality of concepts and relations obtained in this manner is utterly lacking in logical unity. In order to supplement this deficiency, one invents a system poorer in concepts and relations, a system retaining the primary concepts and relations of the first layer as logically derived concepts and relations. This new secondary system pays for its higher logical unity by having as its own elementary concepts of the second layer, only those which are no longer directly connected with the complexities of the sense experiences. This is an object sense, in a sense. Further striving for logical unity brings us to a tertiary system, still poorer in concepts and relations, for the deduction of the concepts and relations of the secondary, and so indirectly of the primary layer. Thus the story goes on until we have arrived at the system of the greatest conceivable unity and of the greatest poverty of concepts of the logical foundations, which are still compatible with the observation made by our senses. We do not know whether or not this ambition will ever result in a definite system. If one is asked for his opinion, he is inclined to answer no. While wrestling with the problems, however, one will never give the hope that this greatest of all aims can really be attained to a very high degree. An adherent to the theory of abstraction or induction might call our layers degrees of abstraction, but I do not consider it justifiable to veil the logical independence of the concept from the sense experiences. Here, this is a very strong statement of mathematical Platonism, and reflects a very strong mathematical Platonism, as most thinkers over time that are considered relevant technical philosophers do, because it's logical. It's logical to arrive at that, and it's pretty great, and it's fair. It's fundamentally fair, and meaning equitable, and meaning efficient in reason to arrive at this kind of thing. Because otherwise everyone would be making up their own, and that would just be like this theory of gravity. It's a higher abstraction of theory. The relation is not analogous to that of soup to beef, but rather of wardrobe number to overcoat. Number sense. The layers are furthermore not clearly separated. It is not even absolutely clear which concepts belong to the primary layer. As a matter of fact, we are dealing with freely formed concepts which, with a certainty sufficient for practical use, are intuitively connected with complexities of sense experiences in such a manner that in any given case of experience, there is no uncertainty as to the applicability or non-applicability of the statement. Now, Einstein has been freely philosophizing in this section as he began. The essential thing is the aim to represent the multitude of concepts and theorems close to experience as theorems, logically deduced to belong to a basis, as narrow as possible of fundamental concepts and fundamental relations which themselves can be chosen freely, axioms. So he's talking about inferences as follow derivations, as follow definitions, or axioms, and as calling those theorems and axioms, inferences, as after the rules, and his strategy and tactics as if to achieve a gain as in a game, but logic and for philosophy. The liberty of choice, however, is of a special kind. It is not in any way similar to the liberty of a writer of fiction. Rather, it is similar to that of a man engaged in solving a well-designed word puzzle. He may, it is true, propose any word as a solution, but there is only one word which really solves the puzzle in all its forms. It is an outcome of faith that nature, as she is perceptible to our five senses, takes the character of such a well-formulated puzzle. The successes reaped up to now by science do, it is true, give us certain encouragement for this faith. All right. The multitude of layers discussed above corresponds to the several stages of progress which have resulted from the struggle for unity in the course of development. Everyone can share the same philosophy of science and not agree on pretty much anything else. It's called individuality. They don't. It's called individuality. But they can agree on anything else. It's called communication in individuals. The multitude of layers discussed above corresponds to the several stages of progress which have resulted from the struggle for unity in the course of development. As regards the final aim, intermediary layers are only of temporary nature, or they're ad hoc, or they reflect that there's many ways to the top. It's just a long way, any way you go. They must eventually disappear as irrelevant. We have to deal, however, with the science of today, in which these strata represent problematic partial successes which support one another, but which also threaten one another, because today's systems of concepts contain deep-seated incongruities which we shall meet later on. It will be the aim of the following lines to demonstrate that what paths the constructive human mind has entered in order to arrive at a basis of physics which is logically as uniform as possible. Now I just call all theory A theory, and then capital A theory, and then capital T, A theory, A for the first letter of the alphabet, and A for all, and it's the theory, and then the idea of these things like the context of an object is everything that it is not, that when this context is always vacillating, because it's a variable, it's a constant variable, okay? It's the same, establishes the idea of how there can be something rather than nothing, and all these talks up after the philosophy. It's very regular, it's totally old fashioned, it's very retro classical. It's called strong mathematical Platonism. It's arrived at, all these truths show up, and there aren't any paradoxes. There whatever is an incongruity or paradox just indicates that there are either undefined assumptions, that it is some form of enthymeme, or that it's a fallacy in reasoning. So that otherwise it's built up that those are the desiderata of the finding the right tools in the mathematical models to equip the physical models via physical interpretation, the attachment of the objects to the objects in the models, their behaviors. That's all one thing. Just like if there's a physics that's the laws apply everywhere, mathematics has one too, and logic has one too. And not everybody has the same one because we all have different views of same, but they need not differ. It will be the aim of the following lines to demonstrate what paths the constructive human mind has entered in order to arrive at a basis of physics which is logically as uniform as possible. So, and then the next section is, he says, mechanics and the attempts to base all physics upon it. And it might really reflect in the notion that there's geometry and the attempts to base all mathematics upon it. And there's about 10, 15, 20 pages here. And then he enters the section 3 is called the field concepts. And so these kind of deserve these later reading. And then the theory of relativity. And then, he gets into, one sets up the field equations as the gravitational and remaining character RIK minus 1/2 GIKR equals negative TIK, where R represents the scalar of Riemannian curvature, TIK the energy tensor of the matter in the phenomenological representation. The left side of the equation is chosen in such a manner that its divergence disappears identically. The resulting disappearance of the divergence of the right side produces the equations of motion of matter. This is where there's two notions of state. How things stays the same and how things change. That physics is to entertain both, with regards to nothing is ever really at rest and nothing ever is really in motion, but everything is really at rest in its frame and everything is really in motion in its moving frame. That these theories of potential are to add up all those propensities up above and maintain a continuum of them, while it's just at the same time that the continuum reflects both the infinitesimally different from any measurement and absolutely distinct difference of any two measurements. And so here it's just an exercise in reducing in terms. And as we discussed a little bit, it's like reducing in terms is great and unification is great, but sometimes it subsumes the pseudo, the quasi, or the underneath, the that the really needs to add back in to explain why then what's really being modeled is as of a change or as of a transition, instead of as of a symmetry and a conservation, that it's as of a conservation above after continuity of the exchange. That physics is an open system, physics is a closed system. It's complementary. Recently, however, I discovered in collaboration with Dr. Rosen that the above-mentioned simplest combination of the field equations of gravitation and electricity produces centrally symmetrical solutions which can be represented as free of singularity. The well-known centrally symmetrical solutions of Schwarzschild for the pure gravitational field and those of Reissner for the electric field with the consideration of its gravitational action. We shall refer to this shortly in the paragraph next but one. In this way, it seems possible to get for matter and its interactions of pure field theory free of additional hypotheses. One, moreover, whose test by submission to facts of experiments does not result in difficulties other than purely mathematical ones, which difficulties, however, are very serious. Well, that seems to explain a little bit what goes on. It's called condensed matter physics. Einstein, Podolsky, Rosen, EPR effect, superfluidity, very, very cold stuff. For more than 2 decades, physicists tried vainly to find a uniform interpretation of this quantum character of systems and phenomena. Such an attempt was successful about 10 years ago through the agency of 2 entirely different theoretical methods of attack. We owe one of these to Heisenberg and Dirac, and the other 2 to Broglie and Schroedinger. The mathematical equivalence of the 2 methods was soon recognized by Schroedinger. I shall try here to sketch the line of thought of de Broglie and Schroedinger, which lies closer to the physicist method of thinking. Shall accompany the description with certain general considerations. Now, I'm very, very happy to hear that, because it helps explain why, when it's so often referred to that Einstein was adamantly against the indeterministic nature of quantum mechanics, or that dice rolling in the indeterministic is not a thing, according to the physicist, him, that he leans not just on Schrodinger, who says, well, at least it's a wave, but also to Bohm and then here de Broglie, who also have that, also it's real, this wave, even if it's extra local. And so that the spooky action at a distance is the other thing. He's like, I don't believe in spooky action at a distance, is that he's trying to remove the spooky element of it, because it kind of spooks him out that there is this, but at the same time he has to accommodate it because he's a physicist. That's my reading of his reading. Question is, first, how can one assign a discrete succession of energy value h sub alpha to a system specified in the sense of classical mechanics? The energy function is a given function of the coordinates q sub r and the corresponding momenta p sub r. Well, we've been reading the path integral here a lot, about from Feynman and from Swanson's book that details the current sort of development of the academic linear curriculum of a development of the path integral mathematically to make it so that Feynman diagrams all add up and all this kind of stuff. And so it is in terms of the Heisenberg picture and the position of momenta. According to Heisenberg, uncertainty, one or the other is off a bit, but that it has one, it has a position, it has momentum in any time, a thing. And then he says, Einstein, Planck's constant h relates the frequency h alpha over h to the energy values h alpha. And this is part of the discretization, because Planck's constant is a small quantity related to the small quantity of the electron physics. When we've been talking about Feynman and quantum electrodynamics being mostly all about the electron physics, that after Millikan, after Thomson, that it was discovered the electron has mass ... And later when it discovered the proton, it's like the electron's mass is 1/2000th proton. And this kind of thing. That Planck's constant is just relating this the frequency to that to give it a fixed frequency as well, because as a wave, it has waves and it's more. It is therefore sufficient to give the system a succession of discrete frequency values. See, now the idea is not so much, that's the whole point of this harmonic and hyperharmonic, is that this discrete has representations in the spectral, and in the spectrum, what happens when it's diffracted, this discrete, into this upper harmonic and hyperharmonic, it is, this theory of potentials, that then this theory of sum potentials and theory of omega potentials has that omega in the limit, in the continuum limit, that becomes continuous again. So here Einstein is just saying, hey, I want to frame this out, and here's our tools we have, and so he's relating the setup here is from that time, how he's approaching the wave function of Schrodinger and de Broglie for particle action. This reminds us of the fact that in acoustics, a series of discrete frequency values is coordinated to a linear partial differential equation if boundary values are given, namely the sinusoidal periodic solutions. Right. This is classical wave action. In corresponding manner, Schrodinger set himself the task of coordinating a partial differential equation for a scalar function psi to the given energy function E QRPR, where the QR and the time t are independent variables. In this he succeeded for a complex function psi in such a manner that the theoretical values of the energy h sub, and I've been reading it alpha, but it's h sub sigma, a little sigma, which should be the sum usually. If little sigma is for big sigma, is this summand and the sum, as required by statistical theory, actually resulted in a satisfactory manner from the periodic solution of the equation. And so he's explaining that for the mensuration and from over time and the value of this energy, and that has to add back up from the transport of a quantity as a wave-like particle called a wave packet, photons called a wave packet, or as part of a wave, and then it's detected in terms of the discretization that occurs as what is for denormalization and renormalization. The reason that renormalization is so great and adds back up to finite terms is because it was obliterated into the discretized and made a point-like representation. Here he's explaining that this would be a good useful thing to offer sort of an approach to a method for building out in these, what's to do these days is the harmonic functions in these, that this is what it is today, these days. To be sure, it did not happen to be possible to associate a definite movement in the sense of mechanics of material points with a definite solution psi q sub rt of the Schrodinger equation. This means that the psi function does not determine at any rate exactly the story of the q sub r as functions at the time t. And here when he indicates with emphasis exactly, this means that the psi function does not determine with at any rate exactly, dot, dot, dot. And it kind of makes me think of when he talks about special relativity and he says the E equals mc squared is inexactly. And so, and then it also has with regards to special relativity that is expressing that special relativity is local. We can read that as not contradicting with this out of context quote from Einstein, which is nice. The story of the q sub r, the momenta, as functions of the time t. According to Born, however, an interpretation of the physical meaning of the psi functions was shown to be possible in the following manner. Psi, the square of the absolute value of the complex function psi, is the probability density at the point under consideration, the configuration space of the q sub r at the time t. It is therefore possible to characterize the content of the Schrodinger equation in a manner easy to be understood but not quite accurate as follows. It determines how the probability density of a statistical ensemble systems varies in the configuration space with the time. Here at least see these the time. Briefly, the Schrodinger equation determines the alteration of the function psi of the q sub r with the time. Well, all right. I mean, this is kind of what I can read from this today, and but they'll be going back over this because I'd like to kind of read this more thoroughly and through. He has later in this section, which is the section. Here's section 5 in this book in his book, Quantum Theory and the Fundamentals of Physics. He has this quote near the end, and he usually ends his sections and works with nice summatory, conclusive statements or something nice, To be sure, it has been pointed out that the introduction of a space-time continuum may be considered as contrary to nature in view of the molecular structure of everything which happens on a small scale. Not if it's really continuum mechanics and we're just discretizing points. As long as it's conscious that it's really a continuum mechanics that our particle mechanics is attains to in the limit, it is sure that can be pointed out, yes. It is maintained that perhaps the success of the Heisenberg method points to a purely algebraical method of description in nature that is to the elimination of continuous functions from physics. That would be wrong because retrofinitists are absent understanding that there's continuum mechanics. Then, however, we must also give up by principle the space-time continuum. It is not unimaginable that human ingenuity will someday find methods which will make it possible to proceed along such a path. At the present time, however, such a program looks like an attempt to breathe in empty space. So Einstein is saying no. There's no doubt that to retrofinitism. There's no doubt that quantum mechanics has seized hold of a beautiful element of truth, and that will be a test stone for any future theoretical basis, in that it must be deducible as a limiting case from that basis, just as electrostatics is deducible from the Maxwell equations of the electromagnetic field, or as thermodynamics is deducible from classical mechanics. And here that classical mechanics is deducible from potential mechanics, continuum mechanics. However, I do not believe that quantum mechanics will be the starting point in the search for this basis, just as vice versa, one cannot go from thermodynamics, respectively, statistical mechanics, to the foundations of mechanics. So he's suggesting that what we need to read more is about the foundations of theoretical kinematics, mechanics. In view of this situation, it seems to be entirely justifiable seriously to consider the questions as to whether the basis of field physics cannot by any means be put into harmony with the facts of the quantum theory. Here his field physics or his space-time's physics. They can. They must be. There are no paradoxes. We must attain to that, and it must be so in the limit. Is this not the only basis which, consistently with today's possibility of mathematical expression, can be adapted to the requirements of the general theory of relativity? The belief prevailing among the physicists of today that such an attempt would be hopeless may have its roots in the unjustifiable idea that such a theory should lead as a first approximation to the equations of classical mechanics for the motion of corpuscles, or at least to total differential equations. As a matter of fact, up to now, we have never succeeded in representing corpuscles theoretically by free fields of singularities, and we can, a priori, say nothing about the behavior of such entities. One thing, emphasis Einstein's, however, is certain. If a field theory results in a representation of corpuscles free of singularities, then the behavior of these corpuscles with time is determined solely by the differential equations of the field. The notion of the singularity might be that this is the idea of the white holes everywhere in space-time, just like the Dirac positronic sea is that, well, after quantum theory, according to Dirac, the whole space-time is everywhere in its field is a vanishing positron and a positron pair that never does anything, just in case things blink in and out of existence. It's still so. And then similarly, this idea of the white holes everywhere is like, well, when you get thinking about the original basis and the free analysis about the origin of coordinate spreadings, then for Einstein, he can have like basically a little teacups car. What's a teacups car? Well, if you've ever been to an amusement park, there might be a little ride called a teacups car. And what it is it's a ride, and what it is that there's a spinning disc, and so everything comes to a stop, and then there's a series of a circle of arranged cars, and each person gets in their car, or each party gets in a separate car, and kind of fills up the cars, or depending how many people there, right? And so as that spins around, then it's applied energy to start the entire apparatus spinning around, and then each car can also spin independently inside that. So that's kind of what singularities are in terms of that. When we were talking about general relativity before, and it's like, yeah, everything is straight, it goes straight down. Let's not talk about the rotational, because we get into torsion and anti-de Sitter space, and why Rindler is the road reality. And Rindler is really a great explicator and a builder. Rindler and the road reality, and Rindler, and furthermore, Rindler's works in torsion, big. But anyways, in this teacups ride is just a general metaphor, kind of going along with this train track that Einstein. First of all, we have Einstein's train tracks and Einstein's train stations, and this reflects, first off, it's classical, right, to the first order approximation, and it reflects all that kind of stuff. Secondly, it reflects his notions of coming and going and this and that. Then the idea is that there's a teacup setting in the train cars, and that the teacup's handle can move around the saucer as it goes. Here is a suitable milieu for an Einstein's Gedanke in a thought experiment. Why there are, in a direct positronic sea, white holes everywhere, making for rotating frames that help keep relativity consistent and free of some of these contradictions that might so arise about the rotational, and keep Einstein's main principles and especially mass energy equivalence and his contribution to that about the rotational, and then also of the cosmological constant, mostly about that. Then that as well, it makes it so that for this continuum mechanics that these things can be so defined, and then for the dynamical modeling and modes of centrality and systems over time and the free rotation with respect to that maintaining at the same time one centroid of its mass and otherwise with regards to gravity and all these other fields and dot dot dot. That's the sort of thing that makes for continuum mechanics a simple enough accoutrement of a lack of something or a decomposition in the space-time, which makes for free analysis is about that. We're representing corpuscles theoretically by fields free of singularities because they're all one system of singularities in a sense. And we can a priori say nothing about the behavior of such entities. Einstein is a generous and grandiose hedge. Well, anyways, that's kind of why when we read Einstein, it's good to get it directly from the man in his words because he's pretty good at that. And because he was in the world of the day of that, and it was paramount the outcomes of these things, and his efforts toward total field theory make clear his desiderata and requirements of a physics for a physicist as defined by Einstein to partake in any theory and what would apply to anything that's established in Einstein's formalisms. Now I'm looking at Heisenberg, and that's something kind of next to look at because the high energy particle physics and everything to do with the particle acceleration and nuclear physics of the particle models kind of comes up with that. Like Chapter 3, Section 1, radioactivity. Not to be confused with the radio spectrum of electromagnetic broadcasts and radiation, but part of that about nuclear reactions. Well, all right. Hey, have a great day. I hope this was enjoyable. If I might read some more from Einstein, yeah, that would be good. Just kind of sum it up a bit more, because what we talked about is kind of, first of all, his definitions of special and general relativity, And secondly, then the following kind of chapters is about this and that. And then another chapter 2 and about this and that. And then this. So what we'll get into is kind of closing that off, and at the beginning of this summary work, out of my later years, and the end represent kind of his place in the world, and the world was his oyster in a sense, because the world loved Einstein, by and large, and then we'll get from that to where then that will be basically an establishment of them from my perspective, because as a grandiose hedge myself, everything should fit. That this A theory is then just to be marked out and shown how it's all correct and this kind of thing, and that this dually self-inferent consistency, or there is no paradoxes, is a thing we attain to, and Einstein does also. And then that his later years field theory is very much a continuum mechanics, that insofar as you can provide mathematical models that so equip it, he's prepared to integrate into his models, automatically equipping them the same. And then, as it were, so far about the teacups, and that the teacup on the train has a handle and it's free to spin around. But when it's at your face, it's in one orientation. And this is a good set. So anyways, have a great day. So long.